Glass is a non-crystalline solid that is often transparent, brittle, and chemically inert. It has widespread practical, technological, and decorative use in, for example, window panes, tableware, and optics. Glass is most often formed by rapid cooling, quenching of the molten form. Some glasses, such as volcanic glass, are naturally occurring. The most familiar and historically the oldest types of manufactured glass are silicate glasses, based on the chemical compound silica, silicon dioxide or quartz, the primary constituent of sand. Soda lime glass, containing about 70% silica, accounts for around 90% of manufactured glass. The term glass in popular usage is often used to refer only to this type of material, although silica-free glasses often have desirable properties for applications in modern communications technology. Some objects, such as drinking glasses and eyeglasses, are so commonly made of silicate-based glass that they are simply called by the name of the material. We have a picture of a glass building facade. Despite being brittle, buried silicate glass will survive for very long periods if not disturbed, and many examples of glass fragments exist from early glass-making cultures. Archaeological evidence suggests glass-making dates back to at least 3600 BC in Mesopotamia, Egypt, or Syria. The earliest known glass objects were beads, perhaps created accidentally during metalworking or in the production of Faience, okay. Due to its ease of formability into any shape, glass has been traditionally used for vessels such as bowls, vases, bottles, jars, and drinking glasses. In its most solid forms, it has also been used for paperweights and marbles. Glass can be colored by adding metal salts or painted and printed with vitreous enamels, leading to its use in stained glass windows and other glass art objects. The refractive, reflective, and transmission properties of glass make glass suitable for manufacturing optical lenses, prisms, and optoelectronic materials. Extruded glass fibers have applications such as optical fibers in communications networks. Thermal insulating material when matted as glass wool so as to trap air, or in glass fiber reinforced plastics, fiberglass. Microscopic structure. Main article, structure of liquids and gases. The standard definition of a glass or vitreous solid is a non-crystalline solid formed by rapid melting, quenching. However, the term glass is often defined in a broader sense to describe any non-crystalline amorphous solid that exhibits a glass transition when heated to a liquid state. Glass is an amorphous solid, although the atomic scale of structure of glass shares characteristics of the structure of a supercooled liquid, glass exhibits all the mechanical properties of a solid. As in other amorphous states, the atomic structure of glass lacks the long-range periodicity observed in crystalline solids due to chemical bonding constraints. Glasses do not possess a high degree of short-range order with respect to local atomic polyhedra. The notion that glass flows to an appreciable extent over extended periods of time well below the glass transition temperature is not supported by empirical research or theoretical analysis. See viscosity in solids. Oh, am I recording? Yeah. Where was I? Though atomic motion at glass can be observed, and a viscosity on the order of 10 to the 17th minus 1018 Pascal measured in glass, such a high value reinforces the fact that glass would not change shape appreciably over even large periods of time. Zoom in a little bit. There you go. Formation. Oh, I forgot that the amorphous structure of glassy silica SiO2 in 2 dimensions. No long-range order is present, although there is local ordering with respect to the tetrahedral arrangement on the oxygen O atoms around the silicon atoms. Microscopically, a single crystal has atoms in a near-perfect periodic arrangement. A polycrystal is composed of mainly microscopic crystals, and an amorphous solid such as glass has no periodic arrangement, even microscopically. Formation of a supercooled liquid. For melt quenching, if the cooling is sufficiently rapid relative to the characteristic crystallization time, then crystallization is prevented, and instead the disordered atomic configuration of the supercooled liquid is frozen into the solid state at Tg. The tendency of a material to form glass while quenched is called a glass forming ability. This ability can be predicted by the rigidity theory. Generally, a glass exists in a structurally measurable state with respect to its crystalline form, although in certain circumstances, for example in atactic polymers, there is no crystalline analogue of the amorphous phase. Unsolved problem in physics. What is the nature of the transition period? The nature of the transition between a fluid or regular solid and a glassy phase. The deepest and most interesting unsolved problem in solid-state theory is probably the theory of nature in glass and the glass transition. That's from P.W. Anderson. Glass is sometimes considered to be a liquid due to... Oh, I read that. Did I? I don't think so. Glass is sometimes considered to be a liquid due to its lack of first-order phase transition, where certain thermodynamic variables such as volume, entropy, and enthalpy, that doesn't sound like a word, are discontinuous through the glass transition range. The glass transition may be described as analogous to a second-order phase transition where the intensive thermodynamic variables such as thermal expansivity and heat capacity are discontinuous. However, the equilibrium theory of phase transformations does not hold for glass, and hence the glass transition cannot be classified as one of the classical equilibrium phase transformations in solids. Occurrence in nature. Glass can naturally form from volcanic magma. Obsidian is a volcanic glass with high silica content formed from when felsic lava extruded from a volcano cools rapidly. Type is a form of glass formed by the impact of a meteorite, where moldavite found in Central and Eastern Europe, and Libyan desert glass found in areas in the Eastern Sahara. The deserts of Eastern Libya and Western Egypt are notable examples. Vitrification of quartz can also occur when lightning strikes sand, forming hollow, branching root-like structures called fulgurites. Trinitite is a glassy residue formed from the desert floor and at the Trinity nuclear bomb test site. Iguawi glass found in South Africa is proposed to originate from Pleistocene grassland fires, lightning strikes, or hypervelocity impact by one or several asteroids and comets. Here we have a piece of volcanic obsidian glass, moldavite, a natural glass formed by meteorite impact from Besadina. Tube. Naturally occurring obsidian glass was used in Stone Age societies as it fractures along very sharp edges, making it ideal for cutting tools and weapons. Glass making dates back at least 6,000 years before humans had discovered how to smelt iron. Archaeological evidence suggests that the first true synthetic glass was made in Lebanon and the coastal North Syria, Mesopotamia, or ancient Egypt. The earliest known glass-making objects of the mid-Lebanon and the coastal 3rd millennium BC were beads, perhaps initially created as accidental byproducts of metalworking. That's a rude word. Or during the production of that. It's the one that I did before. A pre-glass vitreous material made by a process similar to glazing. Early glass was rarely transparent and often contained impurities and imperfections, and is technically finance. No. Rather than true glass, which did not appear in the 15th century BC. However, red-orange glass beads excavated from the Indus Valley civilization, dated before 1700 BC, possibly as early as 1900 BC, predate sustained glass production, which appeared around 1600 BC in Mesopotamia and 1500 BC in Egypt. During the late Bronze Age, there was a rapid growth of glass-making technology in Egypt and Western Asia. Archaeological finds from this period include coloured glass ingots, vessels, and beads. Much early glass production relied on grinding techniques borrowed from stoneworking, such as grinding and carving glass in a solid state. Your mother. Roman cage cup from the 4th century BC. I'll zoom in on that. The term glass developed in the late Roman Empire. It was the Roman glass-making centre at Trier, located in current-day Germany, that the late Latin term glycum originated, probably from a Germanic word for transparent, lustrous substance. Much like glass objects have been recovered across the Roman Empire in domestic, furry, and industrial contexts, as well as trade items in marketplaces and distant provinces. Examples of Roman glass have been found outside of the former Roman capital in China, the Baltics, the Middle East, and India. The Romans perfected cameo glass, produced by etching and carving through fused layers of different colours to produce a design in relief on the glass object. In post-classical West Africa, Benin was a manufacturer of glass and glass beads. Glass was used extensively in Europe during the Middle Ages. Anglo-Saxon glass had been found across England during archaeological excavations of both settlement and cemetery sites. From the 10th century onwards, glass was employed in stained glass windows of churches and cathedrals, with famous examples at the Chartres Cathedral and the Basilica Saint Denis. By the 14th century, architects were designing buildings with walls of stained glass, such as Saint Chapelle, Paris, and the east end of Gloucester Cathedral. With the change in architectural style during the Renaissance period in Europe, the use of large stained glass windows became much less prevalent, although glass had a major revival with Gothic revival architecture in the 19th century. Windows in the choir of the Basilica of St. Denis, one of the earliest uses of extensive areas of glass. Early 13th century architecture with restored glass of the 19th century. During the 13th century, the island of Murano, Venice, became the centre for glass-making, building on medieval techniques to produce colourful ornamental pieces in large quantities. Murano glass makers developed the exceptionally clear, colourless glass cristallo, so called for its resemblance to natural crystal, which was extensively used for windows, mirrors, ships, lanterns, and lenses in the 13th, 14th, and 15th centuries. Enameling and gliding on glass vessels was perfected in Egypt and Syria. Towards the end of the 17th century, Bohemia became an important region for glass-making production, remaining so until the start of the 20th century. By the 17th century, glass in the Venetian tradition was also being produced in England. Well, in about 1645, George Ravenscroft invented lead crystal glass, with cut glass becoming fashionable in the 18th century. Ornamental glass objects became an important art medium during the Art Nouveau period in the late 19th century. Throughout the 20th century, new mass production techniques led to widespread availability of glass in much larger amounts, making it practical as a building material, enabling new applications of glass. In the 1920s, a mold etch process was developed, in which glass was etched directly onto the mold, so that each cast piece emerged from the mold with the image already on the surface of the glass. This reduced manufacturing costs, and combined with wider use of coloured glass led to cheap glassware in the 1930s, which later became known as Depression glass. In the mid-1950s, Huntington Bros, England developed the float glass process, producing high-quality distortion-free flat sheets of glass floating in molten tin. Modern multi-story buildings are frequently constructed with curtain walls made almost entirely of glass. Laminated glass has been widely applied to vehicles for windscreens. Optical glass for spectacles has been since used in the Middle Ages. The production of lenses has become increasingly proficient, aiding astronomers as well as having other application in medicine and science. Glass is also employed as the aperture cover in many solar energy collectors. In the 21st century, glass manufacturers have developed different brands of chemically strengthened glass for widespread application in touchscreens for smartphones, tablet computers, and many other types of information appliances. These include Gorilla Glass, developed by and manufactured by Corning AGC Inc.'s Dragon Trail and Schlatt AG's Zensation. Glass is in a widespread use at physical properties optical. In optical systems, due to its ability to reflect and transmit light following geometrical optics. The most common and oldest application of glass optics are lenses, windows, mirrors, and prisms. The key optical... Is there someone outside? I don't think so. Was I talking about glass? Optical glass typically has a refractive index of 1.4 to 2.4 and an Abbe number, which characterizes dispersion of 15 to 100. Refractive index may be modified by high-density refractive index increases or low-density refractive index decreases additives. Glass transparency results from the absence of grain boundaries which diffuse scatter light in polycrystalline materials. Semi-opacity due to crystallization may be induced in many glasses by maintaining them for a long period of time at a temperature just insufficient to cause fusion. In this way, the crystalline devitrified material known as Reamer's glass porcelain is produced. Although generally transparent to visible light, glasses may be opaque to other wavelengths of light, while silicate glasses are generally opaque to infrared wavelengths, with a transmission cutoff at about 4 mu meters heavy metal fluoride and chalcogenic genide glasses are transparent to infrared wavelengths of 7 to 18 small meters. The addition of metallic oxides results in different colored glasses, and the metallic ions will absorb wavelengths of light corresponding to specific colors. The manufacturing process, glasses can be poured, formed, extruded, and molded into forms ranging from flat sheets to highly intricate shapes. The finished product is brittle, but can be laminated or tempered to enhance the durability. Glass is typically inert, resistant to chemical attack, and can mostly withstand the action of water, making it an ideal material for the manufacture of containers for foodstuffs and most chemicals. Nevertheless, although usually highly resistant to chemical attack, glass will corrode or dissolve under some conditions. The materials that make up a particular glass composition have an effect on how quickly the glass corrodes. Glasses containing a high proportion of alkali or alkaline earth metals are more susceptible to corrosion than other glass composites. Glass can be fairly easily melted and manipulated with a heat source. The density of glass varies with chemical composition, with values ranging from 2.2 grams per cubic centimeter for fused silica or 2.7 grams per cubic centimeter for dense flint glass. Glass is stronger than most metals. Glass metal? What? Is glass a metal? With a theoretical tensile strength for pure fluorous glass estimated at 14 to 35 gigapascals, 2 million to 5,100,000 psi, due to its ability to undergo reversible compression without fracture. However, the presence of scratches, bubbles, and other microscopic flaws lead to a typical range of 14 to 175 megapascals in most commercial glasses. Several processes such as toughening can increase the strength of glass. Carefully drawn out flawless glass fibers can be produced with a strength of up to 11.5 gigapascals. Reputed flow. The observation that old windows are sometimes found to be thicker at the bottom than at the top is often offered as supporting evidence for the view that glass flows over a timescale of centuries, the assumption being that the glass has exhibited a liquid property of flowing from one shape to another. This video is half an hour long so far. Do I have the... I've got the space. Okay. If the video cuts off randomly, that's probably why. Where was I? A 2017 study computed the rate of flow of the medieval glass used in Westminster Abbey from the year 1268. The study found that the room temperature viscosity of this glass was roughly 10 to the 24th PAs, which is about 10 to the 16 times less viscous than a previous estimate made in 1998, which focused on soda lime silicate glasses. Even with this lower viscosity, the study authors calculated that the maximum flow rate of medieval glass is 1 nanometer per billion years, making it impossible to observe in a human time scale. types silicon dioxide SiO2 is at, hold on, how long do I have left? Okay. The common fundamental constituent of glass fused quartz is made from chemically pure silica. It has a very low thermal expansion and excellent resilience to thermal shock, being able to survive immersion in water where red hot, resists high temperatures of 1,000 to 1,500 degrees Celsius and chemical weathering, and is very hard. It also transparent to a wider spectral range than ordinary glass, extending from the visible further into both the UV and IR ranges, and is sometimes used where transparency to these wavelengths is necessary. Fused quartz is used for high temperature applications such as furnace tables, lighting, cubes, melting crucibles, etc. However, its high melting temperature, 1723 C, and viscosity make it difficult to work with. Therefore, normally other substances fluxes are added to lower the temperature and simplify the glass making process. Quartz, sand, silica is the main raw material in commercial glass production. Sodium carbonate, I'm not reading all that. Soda is a common additive and acts to lower the glass transition temperature. However, sodium silica is water soluble, so lime, calcium dioxide generally obtained from limestone, along with magnesium oxide and aluminium oxide, are commonly added to improve chemical durability. Soda lime glasses, lime plus magnesia plus alumina, account for over 75% of manufactured glass, containing about 70 to 74% silica by weight. Soda lime silicate glass is transparent, easily formed, and most suitable for window glass and tableware. However, it has a high thermal expansion and poor resistance to heat. Soda lime glass is typically used for windows, bottles, and light bulbs and jars. Borosilicate glasses, example Pyrex Duran, typically contain 5 to 15% boron trioxide. Borosilicate glasses have fairly low coefficients of thermal expansion. 7,740 Pyrex CTE is 3 point what? As compared to about that for typical soda lime glass. They are therefore less subject to stress caused by thermal expansion, and thus less vulnerable to cracking from the thermal shock. They are commonly used for labware, household cookware, and sealed beam car headlamps. Lead. The addition of lead oxide into silicate glass lowers the melting point and viscosity of the melt. The high density of lead glass, potassium oxide, soda, zinc oxide, and alumina results in high electron density and hence high refractive index, making the look into glassware more brilliant and causing noticeably more spectacular refraction and increased optical dispersion. Lead glass has a high elasticity, making the glassware more workable and giving rise to a more clear ring sound when struck. However, lead glass cannot withstand high temperatures well. Lead oxide also facilitates solubility of other metal oxides and is used in colored glass. The viscosity decrease of lead glass melt is very significant, roughly 100 times in comparison with soda glass. This allows easy removal of bubbles and working in low temperatures, hence its frequent use as an additive in vitreous enamels and glass solders. The high iconic radius of the Pb2 ion renders it highly immobile and hinders the movement of other ions. Lead glasses therefore have a high electrical resistance, about 2 orders of magnitude higher than soda glass. A Pyrex borosilicate glass measuring cup. Aluminosilicate glasses typically contain 5 to 10% alumina. Aluminosilicate glasses tend to be more difficult to melt and shape compared to borosilicate compositions, but has excellent thermal resistance and durability. Oh, that was definitely someone. I heard a noise upstairs. The addition of barium also increases the refractive index. Thorium oxide gives glass a high refractive index and low dispersion, and was formerly used in producing high-quality lenses, but due to its radioactivity, have been replaced by lanthanum oxide in modern eyeglasses. Iron can be incorporated into glass to absorb infrared radiation, but for example in heat-absorbing filters for movie projectors, while cerium 4 oxide can be used for glass that absorbs ultraviolet wavelengths. Fluorine lowers the dielectric constant of glass. Fluorine is highly electronegative and lowers the polarizability of the material. Fluoride silicate glasses are used in manufacture of integrated circuits as an insulator. I just gonna get a drink. Be right back. What did I miss? Glass. Glass ceramics. Glass ceramic materials contain both non-crystalline glass and crystalline ceramic phases. They are formed by controlled nucleation and partial crystallization of a base glass by heat treatment. Crystalline grains are often embedded within a non-crystalline intergranular phase of grain boundaries. Glass ceramics exhibit advantageous thermal, chemical, biological, and dielectric properties as compared to metals or organic polymers. The most commercially important of glass ceramic is their imperviousness to thermal shock. Thus, glass ceramics have become extremely useful for countertop cooking and industrial processes. The negative thermal expansion coefficient of the crystalline ceramic glass can be balanced with the positive CTE of the glassy phase. At a certain point, about 70% crystalline, the glass ceramic has a net CTE near zero. This type of glass ceramic exhibits excellent mechanical properties. It can sustain repeated and quick temperature changes up to 1,000 degrees Celsius. High-strength glass ceramic cooktop with negligible thermal expansion. Fiberglass. Fiberglass, also known as glass fiber reinforced plastic, is a composite material made by reinforcing a plastic resin with glass fibers. It is made by melting glass and stretching the glass into fibers. These fibers are woven together into a cloth and left to set in a plastic resin. Fiberglass has the properties of being lightweight and corrosion resistant and is a good insulator, enabling its use as building insulation material and for electronic housing for consumer products. I need another drink. Glass fiber wool is an excellent thermal insulating material, commonly used in buildings. And plumbing, for example, pipe insulation. And soundproofing. It is produced by forcing molten glass through a fine mesh by centripetal force and breaking the extruded glass fibers into short lengths using a stream of high-velocity air. I lost the spot. The glass fibers are bonded with an adhesive spray, and the resulting wool mat is packed in rolls or panels, non-silicate. Besides common silica-based glasses, many other inorganic and organic materials may also form glasses, including metals, aluminates, phosphates, borates, chalcogenides, fluorides, germanates, tellurites, antimonity. Just gonna skip that bit. Nitrates, carbonates, plastics, acrylic, and many other substances. Some of these glasses, like germanium oxide, in many respects a structural analog of silica. Fluoride, aluminate, phosphate, borate, and that again have physiochemical properties useful for their application in fiber optic waveguides in communication networks and other specialized technological applications. A CDRW, chalcogenides glass, film the basis for a rewritable CD and DVD solid-state memory technology. Silica-free glasses may often have poor glass-forming tendencies. Novel techniques, including containerless processing by aerodynamic levitation, cooling the melt while it floats on a gas stream, or splat quenching, pressing the melt between two metal and may be used to increase the cooling rate or reduce crystal nucleation triggers. Amorphous metals. In the past, small batches of amorphous metals with high surface area configurations, ribbons, wires, films, etc., have been produced through the implementation of extremely rapid rates of cooling. Amorphous metal wires have been produced by spluttering molten metal onto a spinning metal disc. The number of alloys that have been produced in layers with a thickness exceeding 1 millimeter. These are known as bulk metallic glasses. Liquid metal technologies set a number of zirconium-based bulk metal glasses. Batches of amorphous steel have also been produced that demonstrate mechanical properties far exceeding those found in conventional steel alloys. Samples of amorphous metal with millimeter scale. Experimental evidence indicates the system that may undergo a first-order transition to an amorphous form dubbed Q-glass on rapid cooling from the melt. Transmission electron microscopy images indicate that Q-glass nucleates from the melt as discrete particles with a uniform spherical growth in all directions, while X-ray diffraction reveals the isotropic nature of Q-glass. A nucleation barrier exists, implying a interfacial discontinuity or internal surface between the glass and melt phases. Important polymer glasses include amorphous and glassy pharmaceutical compounds. These are useful because the solubility of the compound is greatly increased when it is amorphous compared to the same crystalline compound. Many emerging pharmaceuticals are practically insoluble in their crystalline forms. Many polymer thermoplastics familiar from everyday use are glasses. For many applications like glass bottles, eyewear, polymer glasses, acrylic glass, polycarbonate, or polyethylene terephthalate are a lighter alternative to a traditional glass. Molecular liquids and molten salts. Someone's messaged me on Discord. I'm hungry. Just a sec. Foster's prawn cocktail. Highly recommend. Molecular liquids and molten salts. Have I read that? I don't think so. Molecular liquids, electrolytes, molten salts, and aqueous solutions are... Where's OBS? 52 minutes in. Should I do a part 2? No, I'm nearly done. Different molecules or ions that do not form a covalent network but interact only through weak van der Waals forces or through transitant hydrogen bonds in a mixture of 3 or more ionic species of a dissimilar size and shape. Crystallization can also be difficult. So that the liquid can easily be supercooled into a glass. Examples include a solution of lithium with chloride salt and water molecules, and the composition range for less than 8, and sugar glass or that. Glass electrolytes in the form of badoped Lie-glass and badoped Ba-doped sodium glass have been proposed as solutions to problems identified with organic liquid electrolytes used in modern lithium-ion battery cells. Following the glass batch production section now. Following the glass batch preparation and mixing, the raw materials are transported to the furnace. Soda-lime glass for mass production is melted in glass melting furnaces. Smaller scale furnaces for specialty glasses include electric melters, pot furnaces, and day tanks. After melting, homogenization and refining, removing of bubbles, the glass is formed. This may be achieved manually by glass blowing. This involves gathering a massive hot semi-molten glass, inflating it into a bubble using a hollow blowpipe, and forming it into a required shape by blowing, swinging, rolling, or molding. While hot, the glass can be worked using hand tools cut with shears and additional parts such as handles or feet attached to the welding. Flat glass for windows and similar applications is formed by the float glass process, developed between 1953 and 1957 by Sir Alistair Pilkington and Kenneth Bickerstaff of the UK's Pilkington Brothers, average British name, who created a continuous ribbon of glass in a molten tin bath on which the molten glass flows unhindered under the influence of gravity. The top surface of the glass is subjected to nitrogen under pressure to obtain a polished finish. Container glass for common bottles and jars is formed by blowing and pressing methods. This glass is slightly modified chemically with more alumina and calcium oxide for greater water resistance. Is glass blowing and roboticized glass float glass unloading. Once the desired form is obtained, glass is usually annealed from the removal of stresses and to increase the glass's hardness and durability. Surface treatments, coatings, or laminization may follow to improve the chemical durability. Glass container coatings, glass container internal treatment, strength, toughened glass, bulletproof glass windshields, optical properties, insulated glazing, and anti-reflective coating. New chemical glass compositions or new treatment techniques can be initially investigated in small scale. Laboratory experiments. The raw materials for laboratory scale glass melts are often different from those used in mass production because of the cost factor has a low priority. In the glass laboratory, mostly pure chemicals are used. Care must be taken that the raw materials have not reached with moisture or other chemicals in the environment, such as alkali or alkaline earth, metal, oxide, or that the impurities are quantified loss on ignition. Evaporation losses during glass melting should also be considered during the selection of raw materials. For example, sodium selenite may be preferred over easily evaporating selenium dioxide. Also, more readily reacting raw materials may be preferred over relatively inert ones, such as aluminium hydroxide over aluminia. Usually the melts are carried out in platinum crucibles to reduce the contamination of the crucible material. Glass homogeneity is achieved by homogenizing the raw materials mixture glass batch by stirring the melt and crushing and remelting the first melt. The obtained glass is usually annealed to prevent breakage during processing. Coloring glass may be obtained by addition of homogeneously distributing electrically charged ions or color centries, while ordinary soda lime glass appears colorless in thin selection. Iron 2 oxide impurities produce a green tint in thick sections. Manganese dioxide, which gives glass a purple color, may be added to... Oh, this is the color section, by the way. May be added to remove the green tint given by FeO and chromium 3 oxide. Additives are used in the production of green bottles. Iron 2 oxide, on the other hand, it produces... I hear people. What time is it? Oh, people are getting up. Low concentrations of 0.025 to 0.1% of cobalt oxide. Cu produces rich deep blue cobalt glass. Chromium is very powerful colorizing agent, yielding dark green. Sulfur combined with carbon and iron salts produces amber, ranging from the yellowish almost black. Glass melt can also acquire an amber color from reducing combustion atmosphere. Cadmium sulfide produces imperial red, and combined with selenium can produce, say, shades of yellow, orange, and red. The additive copper 2 oxide produces a turquoise color in glass, in contrast to copper 1 oxide, which gives a dull red-brown color. Iron 2 oxide and chromium 3 oxide additives are often used in the production of green bottles. Cobalt oxide produces a rich deep blue glass, such as Bristol blue glass. Different oxide additives produce the different glass colors: turquoise, copper, purple manganese dioxide, and red cadmium sulfide. Red glass bottle with glass overlay, amber coloured glass, 4-colour Roman glass bowl manufactured 1st century BC. Uses: architecture and windows. Soda lime sheet glass is... Am I still recording? Yeah. Typically used as transparent glazing material. Typically as windows. In external walls of buildings. Float or rolled sheet glass production is cut to size either by scoring and snapping the material, laser cutting, water jets, or diamond bladed saw. This glass may be thermally or chemically tempered, strengthened for safety, and bent or curved during heating. Surface coatings may be added for specific functions, such as scratch resistance, blocking specific wavelengths of light, dirt repellents, or switchable electron chromic coatings. Structural glazings represent one of the most significant architectural innovations of modern times, where glass buildings are now often dominate skylines of many modern cities. These systems use stainless steel fittings countersunk into recesses in the corner of the glass panels, allowing strengthened panes to appear unsupported, creating a flush exterior. Structural glazing systems have their roots in iron and glass conservatives of the 19th century. Glass is an essential component of tableware and is typically... this is the tableware section. For water, beer, and wine drinking. Wine glasses are typically stemware, i.e. goblets are formed from a bowl, stem, and foot. Crystal or lead crystals glass may be cut and polished to produce decorative drinking glasses with gleaming facets. Other uses of glass in tableware include decanters, jugs, plates, and bowls. Wine glasses and other glass tableware, dimpled glass beer pint jug, lead crystal cut glass, a glass decanter, and stopper. Packaging. The inert and impermeable nature of glass makes it a stable and widely used material for food and drink packaging, as glass bottles and jars. Most container glass is soda lime glass, produced by blowing and pressing techniques. Container glass has a lower magnesium oxide and sodium oxide content than flat glass, and a higher silica, calcium oxide, and aluminium oxide content. Its higher content of water insoluble oxides imparts slightly higher chemical durability against water, which is advantageous for storing beverages and food. Glass packaging is sustainable, readily recycled, reusable, and refillable. For electronic applications, glass can be used as a substrate in the manufacture of integrated passive devices, thin film bulk acoustic resonators, and as a hermetic sealing material in device packaging, including very thin, solely glass-based encapsulation of integrated circuits and other semiconductors in high manufacturing volumes. Glass is an important material in scientific laboratories for the manufacture of experimental apparatus because it's relatively cheap, readily formed into required shapes for experiment. Readily formed into required shapes for experiment. Which experiment? Which readily formed into required shapes for experiment. Easy to keep clean, can withstand heat and cold treatment, is generally non-reactive with many reagents, and its transparency allows for the observation of chemical reactions and processes. Laboratory glassware applications include flasks, petri dishes, test tubes, pipettes, glass-lined metallic containers, and for chemical processing, fractionation columns, glass pipes, Schlenk lines, gauges, and thermometers. Although most standard laboratory glassware has been mass-produced since the 1920s, scientists still employ skilled glass blowers to manufacture bespoke glass apparatus for their experimental requirements. I'm not going to try to read those. Glass is a ubiquitous material in optics by virtue of its ability to reflect, and transmit light. These and other optical properties can be controlled by varying chemical compositions, thermal treatment, and manufacturing techniques. The many applications of glass in optics include glasses for eyesight correction, imaging optics, for example lenses and mirrors in telescopes, microscopes, and cameras, fiber optics in telecommunications technology, and integrated optics, microlenses, and gradient index optics, where the refractive index is non-uniform, and find application in example reading optical discs, laser printers, photocopiers, and laser diodes. Art. Glass as art dates to at least 1300 BC, shown as an example of natural glass found in Tutankhamun's pectoral, which also contained vitreous enamel, that is to say, melted coloured glass used on a metal backing. Enamel glass, the decoration of glass vessels with coloured glass paints, has existed since 1300 BC and was prominent in the early 20th century with Art Nouveau glass, and that of the House of Fabergé in St. Petersburg, Russia. Both techniques were used in stained glass, which reached its height roughly from 1000 to 1550, before a revival in the 19th century. The 19th century saw a revival in ancient glass melting techniques, including cameo glass, achieved for the first time since the Roman Empire, initially mostly for pieces in a neoclassical style. The Art Nouveau made great use of glass with those people and that person in the first French movement, producing coloured vases and similar pieces often used in cameo glass or in lustre glass techniques. Louis Comfort Tiffany in America specialized in stained glass both secular and religious, in panels and his famous lamps. The early 20th century saw the large-scale factory production of glass. Art firms such as Waterford and Lalique. Small studios may hand-produce glass artworks. Techniques for producing glass art include blowing, kiln casting, fusing, slumping, pâte de verre, glass forming, hot sculpting, and cold working. Cold work includes traditional stained glass work and other methods of shaping glass at room temperature. Objects made out of glass include vessels, paperweights, marbles, beads, sculptures, and installation art. Portland vase, Roman cameo glass about 5 to 25 AD. Byzantine enamel plaque of St. Demetrios, 100,000, using the Schlenk-Schmelz sunk technique. Emmy marquetry glass vase with clematis flowers, 1890 to 1900. Glass vase by Art Nouveau artist René Lalique. Clara Driscoll Tiffany lamp, La Burnham pattern, C. 1910. A glass sculpture by Dale Chihuly, The Sun, at Garden of Glass exhibition in Kew Gardens, London. I think that's going to be it for this video. If you want to see a part 2, leave a comment and I'll read the references and the external links. Let me know which other glass you'd like me to read next. Have